Okay, I'll start now, I think. Everyone can hear me, right? Should be unmuted. Yeah. Okay. So welcome everyone to the lesson. This will be on waves and optics. This is one of the longer notes I think we've had. As you can see, right, the notes span about 27 pages. It's quite a lot. So um I don't know how long going through will take. Hopefully 1 hour to 1 hour 15, but although it's a lot of content to cover. But we'll see how it goes. Yeah. Okay. So, okay, the first thing we'll start off with is waves. So basically, right, let's say you consider some dropping a pebble into some large pond, right? What you see is that usually there are some ripples that form around, right? These are sort of one form of waves. And the definition of waves is that basically it's sort of a propagating disturbance. So what they do is that they carry energy with them, lah. Means sometimes, but basically its definition is that it's a propagating disturbance from equilibrium, lah. So there are some examples like water ripples of sound and air. These are considered waves, or electromagnetic waves such as light. Lah. Light is also a wave, if you know about that, because basically light is sort of these like oscillating fields, right? There's one electric field like this, and there's one magnetic field, which is perpendicular to it. Lah. This is what light is basically. Yeah. It is a wave actually. So you might have heard of the wave particle duality thing lah. This also applies to light. In fact, it applies to everything lah. There are also things called matter waves, which basically say that matter also behaves like okay, matter also behaves like waves in certain situations. Yeah, yeah. So first thing we'll do is we study some basic properties of waves. So the simplest form of a wave that you know is a sinusoidal wave. And this is because sinusoids are very common in physics. I think you should know that. So the sinusoidally varying quantity can be expressed as this. I won't go through this too much in detail because I think you should know most of these quantities, but basically A is the amplitude. Uh, this lambda is your wavelength, and this K is your angular wave number. That's what we call it. Or sometimes you just call it the wave number. T is the period. F and omega are the frequency and angular frequencies. Sometimes we just call this as the frequency. Most of the time, this will be the case. Then v is the speed of the wave. And because you know the wave travels one wavelength at one period, you have this relationship. Yeah. And you can also derive a relationship between your wave number and your frequency, which is this. And we can rearrange to get this, which is called the dispersion relation. Yeah. So this one you should mostly know by now. This one is kind of basic. Then now we get to this thing, okay? This thing is what we call the wave equation. So basically, sinusoidal waves are not the only types of waves, but it turns out that every wave can be represented as superposition of such waves. Yeah. But the sort of equation that governs all waves, not just sinusoidal waves, is this partial differential equation here. So what this means is that this can be some quantity. This can be any quantity that is sort of wave-like. For example, in string waves, right? Waves that are propagating on a string, right? This would be your displacement. Or if it's something like sound, right? Sound, there's a lot of air and stuff, right? And usually there'll be some regions of high pressure, regions of low pressure, right? This could be a pressure also. Yeah. So basically, this is the equation that tells you, okay, this quantity is a wave, let's say. And the way you solve it is kind of complicated. It's this thing called D'Alembert's method, and it relies on these two substitutions. We won't go into it too much, and you probably don't have to worry about it ever at this SPhO level, at least. But when you go through a derivation, you get this general solution for a wave. And if if you pay attention to the form, right, you would realize that one component is basically some function that's moving to the right. And this one, and another component is another function moving to the left, basically. And this function, right, this function that describes the wave, right, is basically the sum of both, essentially. Yeah. So that's the solution to the wave equation. And the one thing to note is that a basic traveling sinusoidal wave is a special case. So, because as you can see, right, if we let f be this, right, then you get that this is this. And if you apply the dispersion relation from earlier, you can simplify this to get this. So basically, this is just a really special case of it, lah, and it's one of the most important ones, at least. Yeah. So using this solution, we can basically solve for the how the wave will evolve over time if you're given stuff like initial and boundary conditions, lah. So to give an example, right? Suppose you have an infinite string that's released from rest, lah. So something like shown here, lah, you have an infinite string like this, and you release it. So how exactly the wave will evolve, right? We'll omit the derivation, lah, but it's quite easy to show, lah. You can show that the time evolution of the wave will look like this. So what do you think this means? What this means is that each of these components, right? This is how it looks like initially, lah. This is your function that describes it initially. So what it basically does is that it splits into two halves, and one half moves to the left and one half moves to the right, lah. That's what it's basically saying. So if you had to draw the wave function at some, if you had to draw the function at some other point in time, right, you would have maybe something like your left half would have moved something like this, and your right half would move something like this. So then you get the sum of both, lah, which would, I don't really know what it looked like, lah, but yeah, lah, you basically take both of these and you add them together, lah. Yeah. So that's how infinite string evolves from rest, lah. Then a semi-infinite string has a very similar sort of derivation, lah. You can use a similar derivation, but because right here a semi-infinite string is where you impose a condition that one of your points is fixed. So how you exactly solve is that you would take this solution, right, for an infinite string, and you try to match it with one that's for fixed n, lah. And it turns out that all you have, right, is that you can actually consider this whole thing to be an infinite string that has this point here, lah. So you take this point and you take this string, right, and you reflect it over across the wall, lah. And then you can apply this formula to show the time evolution of the wave, lah. So then again, right, you would take this, maybe it's different color. You would take this, right, you split it into half, and then one half would move to the left, one half would move to the right, lah. And this thing can also travel here, lah. So you in a way you sort of have a mirror image that's also present, lah, and it's also able to interact. Yeah. So that's just an example of how to use this wave this here, lah, to sort of derive using the initial and boundary conditions, lah. Another example is standing waves, lah. If we instead we impose two fixed ends like this, right, you can use a similar logic to this to sort of deduce that you can sort of treat your new infinite string, quote unquote, as one that's reflected like this, lah. And of course, like you have to consider the mirror images of the mirror images as well, lah. So apart from that, it will look like that and like that, lah. So then from there, right, you take this, you split it into half. One half will be moving to the right, one half will be moving to the left. Yeah. So you sort of get this thing, lah, which honestly I think you don't need to worry about. But the thing is that this thing is periodic, lah. So instead, let's go back to sinusoidal functions. So usually when you consider standing waves, it's usually sinusoidal functions also, lah. And I think most of the time they'll probably only ask you on sinusoidal functions. So instead of considering the solution to the wave equation, let's instead consider two identical sinusoidal waves that travel in opposite directions. So you'd have something like a wave like this and a wave like this, right? One is they're both moving towards each other, lah. And they each have equal amplitudes, equal phases, and whatever, lah. But the only difference is that one's moving to the left, one's moving to the left, one's moving to the right. So then when you superimpose both of them, right, you get this function here, lah, which is also a sinusoidal function, but instead it's no longer traveling, right? Because you notice that this part doesn't really depend on time. The only thing that depends on time is this part, which sort of controls your amplitude, lah, per se. So then it's basically a sinusoidal function that's fixed in place, but has an oscillating amplitude, lah. And this is what we call a standing wave, lah. So it would look something like this, lah. Maybe your standing wave would look like this, and it would oscillate up and down and back, lah. Something like that. So if you wanted to impose the restriction that the length between two of these is L, right? You can then do some math, and then we can actually get that there are some conditions on the wavelengths in order to satisfy this boundary condition for a sinusoidal wave, which is this. And this should make sense when you look at this picture here. So basically, this sort of illustrates the standing waves that can be formed in a wall, basically. So as you can see, right? Okay, this length is already marked there, right? So in the first case, right, the wavelength is 2L, because you can see it should extend like this. In the second case, it's L. In the third case, it's 2L over 3, because you can see you can split this into sort of 3 parts, right? And then one wavelength is 2L over 3. And then the next case is L over 2, etc. So intuitively, this should kind of make sense. You can sort of think of it as like the nodes and antinodes. Like you must have a node at each end. So because of that, it mandates sort of these wavelengths to be, it mandates these to be the wavelengths for the wave. And we term the wave that's corresponding to n as the nth harmonic. So this is the first, this is the second, etc. Yeah, so that's for 2 fixed ends. Then there's also standing waves that correspond to one fixed end and one open end. So for example, would be something like a sound wave, like you have a pipe that's open at one end, right? And then you want to analyze the pressure, that's the pressure of the air that's inside, something like that, the standing waves that can be formed from the sound waves inside. So if you want to do this, you can instead impose this new condition, and then you can solve using a lot of math, and you can get another restriction on the wavelength, which is this. And it should also make sense if you just think about the nodes and antinodes. This time, right, you have one node that's at the fixed end, because it must be there. And then you have one antinode that's at the end, because the open end sort of guarantees you that you have an open end like this. So yeah, and then this time we term this is the first harmonic, this is the third harmonic, etc. This is just naming. And the wavelengths, I think you should see how they come about. For this first one, obviously one wavelength is 4L, because you need to take this and you repeat it another 3 times. And here is 4L over 3, because you have to extend it like this, cut into third, something like this. Yeah. So I think you should see the pattern. And yeah, you can look through the math yourself, but it should be pretty intuitive, in my opinion, this part. Yeah. Are there any questions so far? Request to go through. Okay, I'll go through the questions later. Okay. Okay, now we go on to string waves. So the most common mechanical wave that you see are string waves. Yeah, like we've previously discussed. And it's an example of a transverse wave. If you don't know what transverse and longitudinal mean, right? Transverse means your displacement is sort of perpendicular to the axis it's on. So something like this. But longitudinal wave is something like in a spring, where your sort of displacement is parallel to the direction of energy, something like that. So string waves are an example of transverse wave. So you can go through the physics yourself, and I have a lot to go through. You can go through the physics yourself, but eventually what you get by the force analysis, right, is you can actually get the wave equation out of the force analysis. So if you get the wave equation out of force analysis, that means you can now associate some velocity to the thing. So because if you recall in the wave equation, right, this thing will be 1 over v squared. So now you can equate 1 over v squared to this. So now you get this v, and this v is the speed of waves that travel on the string. So all you have is that it depends on the tension of the string as well as the linear mass density of the string. So this is a useful formula that you definitely should memorize, and you'll probably have to use it. So here's one example. Apparently this example was in SPhO before. I mean, that was when they were copying questions, but it's good to know. So a uniform string of length L hangs vertically from the ceiling. You're gonna find the time it takes for a wave to travel from the bottom of the string to the top. All you have to do is you use this formula. So what you do is that for some distance x below, for some distance x from the top, right from the bottom, right, the tension here has to be this, because the tension has to support the string that's below. So then because of that, right, there's infinitesimal time it takes for a wave to travel from x up to x plus dx, right? Is this dt is this, which you can calculate to be this. And then all you need to do is you integrate over the length of the string to get the whole time lah. Yeah. So that's just one simple example of using that formula. Okay. Then now we go to energy and intensity. So now that we've discussed about these waves, right, we want to talk about their energy lah. So let's suppose we have a wave in a string that has linear mass density this and tension T lah. So how do you want to calculate the total energy of the wave? There's two components. One is kinetic and one is potential energy. So let me just draw a new diagram, something like this. Okay, this is one infinitesimal segment of the wave lah. So obviously you continue lah. And this is of length dx. So what two components are there? Firstly is kinetic energy, right? This should be pretty obvious. Why? Because this is just half mv squared. Half m is your linear mass density times your distance, right? And notice that it's mu times dx and not dy squared plus dx squared lah. Notice it's not this because you gotta remember that initially at equilibrium, right, this thing is mu dx lah. And what we're assuming is that these infinitesimal segments do not move left or right. So what actually happens is that over here, there's a bit of a stretch lah. So even though it's a stretch, the mass doesn't change lah. So it's still mu dx. And then this is your dou psi dou t squared. Dou psi dou t is basically just the speed at which it's moving lah. Yeah, so this is basically half mv squared. Then where does your potential energy come from? It actually comes from the stretching of the string. So what you have is that the new length of your string upon stretching is this, because that's just this lah, basically. This is just this. And then your restoring force in the string is tension. So if you think about it, right, in order for the length to increase, the tension has to do work lah. So this work is sort of the potential energy that's stored in the segment lah. So then you have du is your tension multiplied by your change in the length, right? So this is basically work done lah. That's the form of potential energy. So then what we're doing is that in our analysis, we are sort of assuming that the height of the wave is negligible compared to its length. So then we can sort of use the first order approximation here, right? Here we make this as 1 plus half that squared. So then you can take it out and then you get this lah. So this is your potential energy lah. So therefore you have your whole energy that's stored in that infinitesimal segment is this lah. So if you wanted to find the energy in the whole wave, right, you would just take this and you integrate it lah. So then you can get the whole energy lah. So here's one example where you want to calculate the time average power of a sinusoidal wave of amplitude A and frequency this lah. So how exactly you do that? You just take this formula and then you would plug it in using this cosine lah, because you know that it's a sinusoidal wave. And you also have this relationship between omega k, tension, and mu. So you can calculate the energy stored in a segment like this. I will just ignore the math, but it should be pretty obvious for it should be pretty easy for you to derive lah. So you get this. Then once you take the time average, right, the key thing to notice is that this is constant, and the time average of this is going to be half. So then your average infinitesimal energy of it over a segment is going to be half of this times its length lah. So then because of that, right, the total energy that's stored in one wavelength is this. Therefore, the power is sort of the energy that's transferred per time. So since you're considering one wavelength, we divide by the period lah, because it travels one wavelength in a period. So the average power is this. That's what you get. Yeah, and one thing to notice about this, right, is that because this is a one-dimensional string, right, you have that your power is proportional to the amplitude squared. So that's for one-dimensional waves. But for three-dimensional waves, right, the analogous quantity that's proportional to square amplitude is intensity lah. So your intensity is defined as the power that the source emits over the surface area, and this is proportional to the amplitude squared. So if you have something like, let's say you have a source over here, right, and it emits light or something like that, right, then at some distance r away, right, because let's say this is emitting power P, right, since energy is conserved, right, and this whole thing is uniform, right, your power must be spread evenly across this sphere that's around the source lah. So then your intensity would be this P over the surface area of the sphere, which is 4 pi r squared. And yeah. And this intensity is proportional to the amplitude squared, lah, which you can also show from the wave equation, but you need to put in 3D. Lah. Yeah. So then because of that, right, from this relation, you can now get that your amplitude of a three-dimensional propagating wave is inversely proportional to its distance. Yeah. So I think that should be about it for waves. There's more content up later about. Actually, I'll just go through it right now. Actually, it's in ideas. I'll just loop back and forth from ideas to the main stuff. So I guess now that we've discussed a little bit about waves, we can talk a little bit about beats and phase and group velocity. So the idea of beats is that basically, right? Okay, you can try this yourself actually. Like you can open two generators and you can play two tones of frequency, 440 and 441. So the thing is that humans can barely actually tell apart these two frequencies. But when you play both of them together, you get a really distinct oscillating variation in amplitude. Like you can hear it go loud and soft, loud and soft. And it turns out that the frequency of the loud and soft, right, is 1 hertz. So this is sort of the concept of beats. And how it works is that because you have two waves, right, that are sort of super close in frequency and wave number, but they're just slightly different only. So then when you add, right, when you add both of the waves together, you sort of get something like this. Like I drew it very badly, but this is something like what it would add up to look like. So you sort of this one component, which is sort of the average frequency of both this, which is honestly basically the same as around 440 lah. And then you have another component, which is sort of this oscillating component lah, right? If you see this, this is the sort of beat frequency that we call lah, and this is the 1 hertz that you see lah. So you can go through the math yourself, a lot of math and stuff, and you eventually get your envelope. This is what we call the envelope lah, sort of lah, because it's sort of the boundary of this like function lah. So we get that this envelope, right, has this frequency lah. So since the intensity is proportional to the square of the amplitude, your intensity is proportional to this, which can be simplified to that. So you can see that your frequency, right, is actually the difference between the frequencies, and you get this thing called the beat frequency. So this explains the 1 hertz beat that you would hear if you did this example, the 440 and 441. Really, I can ask you to try it. You can actually hear the 1 hertz. It's very, very obvious. Yeah. And then this example also leads us to phase and group velocity. I don't really know if you need this in SPhO, but it's good to know because it sort of illustrates an idea that you don't really get from sinusoidal waves, which is that waves might not necessarily have a linear dispersion relation, which looks something like this. They may not necessarily have that. Sometimes it can look something like this. So sometimes you can have really weird dispersion relations. For example, this is for, I think, deep water waves or something like that. So there's actually concept of two velocities. One is a phase velocity and one's a group velocity. So the phase velocity is sort of what we've already discussed about. Your phase velocity is this. So if you think about your constituent wave like this, right, it's moving at some velocity v, this is your phase velocity. But in a wave that's not necessarily sinusoidal, and it can be considered as the sum of sinusoidal waves, right? As you saw with this example, right, the sort of combined behavior of these constituent waves, right, sort of creates this envelope, right, that itself also moves at some velocity, right? So this is sort of called the group velocity, and we define it like this, similar to what we derive from here. So this is the sort of group velocity of the wave that we have, and it's sort of analogous to the velocity of the envelope. Yeah. I don't think you need this in SPhO, but it's good to know. Yeah. And the last thing you probably need to know is Doppler effect. So for Doppler effect, right, basically if you've ever heard like a car horn or an ambulance, right, if it passes by you, right, you might hear the pitch change. So that's something called the Doppler effect. And the frequency doesn't actually change. The frequency of the sort of siren doesn't actually change, but you hear a different frequency because of the fact that if you are approaching the wave fronts, right, you will sort of hit them more often, sort of. So you can go through the math yourself, but it's some very simple wavefront considerations, and you can eventually end up with this, which is your Doppler effect expression, And here we define V observer and V source moving towards each other is positive, So this is your sort of Doppler effect. You can read this yourself, but this is something that you will definitely need to know. Yeah. Okay. At this point, are there any questions about what I've covered? Because I know I'm covering it really quick, because there's a lot of stuff to go through today. Okay, if there's nothing, it's okay. But if there's anything you still need to clarify, you can always read the notes, or you can Google online sources, because I know the notes are not necessarily self-sufficient. Yeah. Okay, now we go on to physical optics. So this is where we start discussing about light. So in physical optics, we discuss light as waves, and as you'll see later, there's another field of optics called geometrical optics, which discusses on light as rays. So first thing we'll consider is physical optics, and it applies when the scale of consideration is comparable to wavelength of light. So first thing we want to discuss is interference. So as we talked about just now, right, there's the concept of wave called superposition, which is basically the reason that they can sort of add up. This is because the wave equation is linear. But basically, you can just think of waves as being able to add to each other, and you get a valid wave. So for example, if you have two overlapping waves that have equal number and frequency, but not necessarily the same amplitude of phase, right? These crests and troughs, right, do not actually occur at the same position. So this is what this, so we can call them out of phase, because they actually have a phase difference. Yeah. Then you can actually determine that the spatial separation between the 2 points satisfies this. It is the equation that you're going to need to know. So like the phase here and the phase, basically there's a phase difference between both of this, and that can be derived by this if you know there's spatial separation. And you also term a wave source coherent if the phase difference between the waves is constant. So basically, a coherent wave source would emit waves something like this, but an incoherent wave source would emit waves that are all out of phase. So then you might not be able to observe stuff like interference and stuff. Yeah. So two special cases, right, are constructive and deconstructive interference. This should be pretty clear cut, because one case is where you have waves that are like this. So when you add, obviously, right, their amplitudes will increase. And the other case is when they're out of phase, something like this. In which case, when you add, right, your amplitude is going to decrease. Yeah. So this is called constructive and deconstructive interference, respectively. And from this formula, right, as well as the fact that you know that phase repeats every 2 pi, right, you get that your path difference of this will sort of allow for constructive interference, and a path difference of this will allow for destructive interference, assuming that both waves are initially in phase, basically. Yeah. Yes. And it might seem to violate the conservation of energy, because if, let's say, you have one wave that's like this, and you have one wave that's like this, right? When they eventually combine, right, what you're going to get is something like this. It's a completely flat string. So you might think there's no more energy left, right? But actually there is energy, because it's stored as kinetic energy. So the wave will actually be like something like this sort of kinetic energy stored in each infinitesimal segment, and that's where the energy has sort of gone. But just remember that superposition doesn't violate conservation of energy. Yeah. So now that you know about interference, right, we get to double slit diffraction, where basically Young conducted an experiment called the Young's double slit experiment to demonstrate that light actually has wave-like properties. So how it works is that we start with a coherent source, right, that sort of emits plane waves, something like this, right? So there's light coming through here, basically. Then what happens, right, is that you have two tiny slits over here that allow light to pass through. So when that happens, right, your light sort of emits radially like this, so that if eventually impinges onto a screen. And usually your expectation is that the light will just pass directly through the slits like this. So then you only get two spots like this. That might be your initial expectation. But it turns out that you actually observe something called diffraction, and your pattern will look something like this. So actually, this is obviously because of the wave nature of light, as we described. So this is a this is something called diffraction, and the pattern formed on the screen is called a diffraction pattern. So why exactly does it occur? It's because of this interference. So let's say we consider some point on the screen over here, and we want to consider two light rays that come from each of these slits. The reason there is intensity is because obviously it must come from each of these slits. But it may either be constructive or destructive depending on their phase difference. Because you gotta remember that since this is coherent, right? The phase of both of the light rays at these points are the same, but they have to travel different distances. So because of that, eventually when they arrive here, they might be out of phase already and have a phase difference. And this phase difference is sort of determined by this distance here. The phase difference, yeah, the phase difference is sort of this distance here, because the first assumption we make is that this length is super, super long compared to the distance between the slits. So because of that, right, we can assume that both of these lines are basically essentially parallel. So then because of that, the only phase difference comes from this extra contribution here, which we can derive to be d sine theta, where this theta is the angle of each ray from the horizontal. So then now that you have this phase difference, right, from there, you can get these conditions. These conditions are for your constructive and deconstructive interference respectively. So this at angles which satisfy this, right, you will have a bright spot on the screen. And for angles to satisfy this, right, you will have a dark spot on the screen. Yeah, I think you should have learned this before, actually. So I think this should not be too unfamiliar. Yeah, and you can also find the maximum number of bright spots. We just use this fact that you can get this. Yeah. So if you want to calculate the positions of the bright and dark spots on the screen, right, you can either do it exactly or you can use another assumption, which is that this angle of the ray is super, super small. So if that's the case, right, you can approximate your sine theta to be about tangent theta. So then you can do the calculations to eventually get these two relations for your bright and dark fringes. So from there, you can get that your sort of distance between each bright fringe, right, this distance, right, is lambda L over D. Yeah. So these are the equations that you ideally should definitely be memorizing for this double slit diffraction. Yeah. So now that we have an idea of now that we have an idea of where the bright spots are, if we want to calculate the intensity, right, a very useful thing that we want to illustrate is phasors. I thought this idea before in the last lesson about AC, RLC circuits. But basically, right, because light is a sinusoid, right, we can express it as phasors again. So if you need a recap of phasors, you can go back to the ACRLC notes and you can recap on what exactly phasors are. But I'll assume you know by now. So what we're going to do is that we suppose that the electric field here is, damn it, we assume that the electric field here, right, is E naught, represented as a phasor. So obviously there's going to be an extra component at the back. Oh, sorry. There's going to be so obviously this means that your actual electric field is going to look like E naught cosine blah blah blah, your kx minus omega t, right? Then because of the phase difference between the two light rays, right, your electric field at the bottom slit, once it reaches here, right, it has this extra phase because of this phase difference. So we represent it as this. So then what we do, right, is that because of the superposition, right, the electric fields will add. So then we get your total electric field over there is this. And then because your intensity is proportional to the square of the amplitude, right, you get your intensity is proportional with this. So once you solve for phi, right, your phi can be determined using this, right? Once you do that, right, you get this is the function of your intensity as a, this is the equation for intensity lah. Your relative intensity compared to the center of the diffraction pattern lah. And that's an example of phases lah. I'm not too sure how, I'm not too sure how likely you need this for SPhO, but it's definitely very good to memorize. Yeah. Okay. Diffraction gratings have a very similar concept, right? Instead of two slits, you have many slits like this, and we call it a grating. And it's characterized by the number of gratings per unit length, which can be used to determine the slit distance, the distance between each slit, basically. And your diffraction pattern looks like this, right? If you compare it to this, maybe it's not so obvious, but but the main thing about a diffraction grating is that usually your peaks are much more distinct. So because for a double slit, right, your intensity looks something like this, something like this. But for a grating, right, your intensity will look super obvious, something like that. You get the idea. But for grating, it should be much more obvious, essentially. And you can apply the same reasoning, because if you apply the same reasoning, right, this here, right, this spatial difference, right, is d sine theta, right? So then you have a phase difference of the same amount, this, right? Then if you apply the condition for constructive interference, you get this, And because, right, if we have this is the case, right, then then in your next case, right, your phase difference of this compared to this is going to be 2d sine theta, And 2d sine theta is also going to be a multiple of lambda. So then you're also going to have constructive interference in there. And then so on and so on and so on. So if you have this condition, right, all your rays are going to constructively interfere and produce a really bright peak. Yeah. So this gives you the bright spot. And the dark spots usually you don't really consider because usually between the bright spots, it's sort of equally dark. So you don't really care too much. So you only probably need to note the bright spots. And similarly, you can use the same reasoning as we had earlier to get your position of the bright spots. And you can also use the same phasor logic instead you need to use a sum, but you can use the same phasor logic to sort of derive the intensity pattern. Yeah, I'll leave you to read the math details. Yeah. For the intensity, please explain why it's divided by n squared. Okay, the reason it's divided by n squared is because you gotta remember the condition that for a grating, right, here, right, your central maximum will occur at the center. This is where theta is 0. So at theta equals 0, this is by definition, your theta equals, at your theta is 0, your intensity is I naught. So because of that, right, this function here, right, it needs to be 0 it needs to be I naught at 0. And sorry, if you notice, right, the function is not actually defined at theta equals 0 because this will evaluate to 0. So your denominator is 0. But what we do is we take the limit as theta approaches 0 and we want to set it to I naught. So to do that, right, because of the small angle approximation, right, your sine, you can sort of think of these signs disappearing because your sine theta is approximately theta, right? So you can get rid of this, get rid of this, your square, get rid of this, it's a square, get rid of this. And you can notice that these two will also cancel with each other, right? So you're left at the limit of small theta, it will look like n theta squared over theta squared. So that's why you need this extra n squared, so that this thing evaluates to 1 at the limit. And this is your I naught here. So yeah. But it's not too important. You probably don't need to memorize the exact form of this expression. I really doubt it. But it's good practice with phasors you need to know. And then Why is this valid for diffraction grating? I thought angles for diffraction grating are usually not. It's valid for in the small lah, but if it's not small, you don't use that formula lah. It's quite easy to derive if you don't want to use the small formula lah, because you have the relationship between tangent. Sorry, I'm trying to find it. You have the relationship between tangent theta and sine theta lah. So what you can do is that you have your d sine theta as this, right? So your sine theta is m lambda over d, right? From here, you can calculate your tangent theta lah, to be your sine, to be your sine theta over cosine theta lah. So once you have your tangent theta, right, then your distance is just this lah. So you can just substitute there lah. So if it's not small angle, then you have to do that lah. You need to take note of which assumptions are valid at any point in time lah, because there are two assumptions that you're taking here lah. One assumption is that this L is much greater than your D, and most of the time, right, this assumption will be true. Your second assumption is that the angle of the ray is small, but sometimes it might not be true depending on the question. So if it's true, right, you can just directly use this lah. But if it's not true, you have to take your sine theta, right? Yeah, you have to take your sine theta, convert it to tangent theta, and then your y is L tangent theta lah. Yeah. So just you need to take note of that lah. Yeah. Okay. Now we go to single slit diffraction, right? So basically, right, just now, this image I showed, right, is actually a real image of double slit diffraction lah. But I kind of cropped it. The full picture is actually here lah. So if you actually pay attention, you notice that there are still these dark spots that appear, actually, which seems quite suspicious because if you look at the intensity pattern for a double slit diffraction, right, this only oscillates at an equal amplitude. So it's equal amplitude lah. So it's very suspicious why it would have these sort of dark spots. But it turns out that these dark spots are actually because of single slit diffraction. And it's because in real life, right, your slits have some finite width lah. And because it is finite width, right, you get this thing called single slit diffraction, or what we call Fraunhofer diffraction also lah. So yeah, so how we would treat the diffraction, how we would find the intensity pattern for single slit diffraction is that you can think of light coming in here, right? You can split this into regions of n regions, right? You can consider one source that's emitted from each, like this. Then what you want to do is that you take that limit as n approaches infinity, and then you get a full single slit diffraction pattern lah. So it turns out that if we split into n regions, right, it's basically the same as a diffraction grating. So we have the intensity pattern is like this. Then if you take the limit as n approaches infinity, right, you notice that these two will sort of cancel each other out in a way. You're this, the limit as n approaches infinity of this bottom part is this part. So because of that, right, you get this lah, which is equivalent to this. And this is the sinc function lah. The sinc function is defined as that. So your intensity, right, by a single slit will look something like, oh, sorry. This is your sinc function lah. This is sinc, right? So your intensity will look something like this lah. So it's square lah, essentially. So yeah, so your single slit diffraction exhibits this sort of intensity pattern that depends on the sinc function lah. And this is a single slit diffraction pattern. And from this formula, you can determine the minimum of the single slit diffraction, right? And it occurs when this argument here is 0. Because when this is, sorry, when the argument here is m times pi, because if it's m times pi, right, your argument to sine is m times pi, which divides to 0. So the minimum of the single slit diffraction pattern can be calculated as this lah. And note that this only applies for m is not 0 lah, because your single slit diffraction pattern actually looks something like this, maybe. I'll just draw it very big. It looks something like this. And because, right, it's minima for every point onwards, right? except the middle. Your middle is actually a maxima lah. So there's no zeroth order minimum lah. There's only a first order minimum, second order minimum, etc. lah. So please take note of this. I didn't actually include it lah. So just take note of this. I'll update the notes with it lah. Yeah. So that's single slit diffraction. And we get to this thing called a Rayleigh criterion, which is basically when you're considering single slit diffraction, right? It might be hard to distinguish two objects from each other lah. So for example, if you have two sources like this, right, they will have diffraction patterns on the screen like this. And if they're too close to each other, right, you notice that their peaks will sort of intersect, right? And that sort of makes it difficult to differentiate lah. So if they're far apart, your sources might look something like this. But if they're close together, it might look something like this lah. And you can usually blur it on the outside lah. But then if it becomes like this, right, it's difficult to sort of resolve the two sources from each other lah. So the Rayleigh criterion describes what needs to be done for them to be resolved lah. And the criterion states that for them to be resolved, right, if you have two diffraction patterns, something like let me see, something like this, it would have to be the maxima, right, sort of resides on the minima of the next. So something like your zeroth order maximum at most must lie on the first order minimum of the other one. So for normal rectangular slits, right, you can determine the condition to be, where is the normal? Condition to be this, where this is your angular hard width between this. But typically we use circular apertures, right? So instead, right, the Fraunhofer diffraction gives a different expression for the intensity lah. But it turns out that you have your Rayleigh criterion for a circular slit is this, where your D is the diameter of the aperture lah. This is a formula I think you need to memorize. So just memorize it lah. Yeah. So if they give a question where they ask you to resolve two sources through a circular aperture, right, and they ask you for an angular hard width, right, you should use this formula lah, basically. Yeah. And the last idea I want to illustrate for physical optics is polarization and thin film interference. So the thing about polarization is that light can exhibit polarization. If you look at this diagram, right, basically, right, I've talked about how light is basically an electromagnetic wave, right? You have an electric field oscillating perpendicular magnetic field, right? So because of this, right, since light is a transverse wave, right, it can have its displacement in any axis lah, basically. So as you can see, the electric field can point in different directions lah, for polarized light. And unpolarized light, which is what you mostly see lah, you haven't passed through a polarizer yet, right? Your unpolarized light, you can sort of treat it as sort of random time varying polarization. It's sort of a uniform mixture of linearly polarized light lah, sort of. So that's the concept of polarization lah, because your electric field can point in any direction lah, sort of. And polarizers are optical filters that allow only one specific polarization of light. So if you have light that's sort of pointing in this direction, right, and you pass it through a polarizer that only allows something like this angle of polarization to pass through, right, then the light that comes out will sort of point in this direction according to the polarizer lah. So that's what a polarizer does. So it only allows the component of the electric field of the light that is parallel to itself, right, to pass through. So because of that, right, your electric field ends up becoming multiplied by cosine theta, where your theta is the angle it makes with the light passes through lah. And since intensity is proportional to the square of the amplitude, you get this lah. And this is what we call Malus's law, basically. So if you have polarized light that passes through a polarizer that's at angle theta, right, the intensity of the light that comes out is multiplied by cosine squared of the theta lah. And the theta is the angle between the polarizer and the polarization of the light that comes into it lah. Yeah. And do know this only applies for polarized light lah. So if you have unpolarized light instead, right, so because it's like this, right, and they pass it through a polarizer, right, you can derive that the intensity that comes out of the polarizer, because it goes from unpolarized to polarized, you have the average of this cosine squared, which is half lah. So your intensity that comes out of the polarizer is half of the intensity of the unpolarized like before lah. Yeah. And light can also actually, so light cannot just be polarized by a polarizer lah. It can also be polarized by passing through an optical medium lah, something like this. So because right, light can either be reflected or refracted, right? Because usually when light enters an optical media, right, which we'll discuss later, your light ray can either be reflected, sorry, not either. It will have a component that is reflected and it will have a component that is refracted, right? So obviously some of the intensity will split lah. And it turns out that both of the reflected and refracted rays are polarized to some extent, sort of. And at some angle of incidence, when the refracted and reflected rays are perpendicular to each other, right? So something like this, right? When it looks like this. When this occurs, right, your reflected ray is actually completely polarized. So because of that, right, we get this thing called Brewster's angle, where basically the Brewster's angle is sort of the angle of incidence such that it's true lah. So when your reflected ray will sort of be completely polarized when this happens at the Brewster angle. Yeah. So that's about polarization. Then the last thing I want to talk about is thin film interference. So we haven't talked about how phase exactly evolves in an optical medium, but the special thing about optical media, right, which we'll explore more in geometric optics, right, is that in an optical media like glass, right, when light enters it, right, it bends. And it bends because the phase velocity of light is actually decreased by a factor of n, where n is the refractive index. So it turns out, right, that this relation is actually changed to include this refractive index. So your phase actually depends linearly on the difference in the optical path lengths of two rays lah. So because of that, we can now we can do some stuff with thin film interference. Or we can, sorry, but there's also one more thing I need to talk about, which is that you definitely need to remember this lah. This is kind of important. So let's say you have a ray in some optical media, something like this. And let's suppose that this N2 is more than N1, right? If light comes in here and there's some component that's reflected and there's some component that's refracted, right? It turns out, right, that this light ray, right, would have undergone a pi radian phase shift at this boundary lah when it reflects. This one won't lah, but this one undergoes a pi radian phase shift. And only if the light that it contacts is in a more optically dense medium. So if you have a situation where instead, right, it hits a less optically dense medium, right? In this case, if let's say it's like this, right, then neither of these encounter a phase shift. So it's only this particular case which is phase shift. And it has to do with the electromagnetic properties of light, which we'll not really discuss. But yeah. So this thing is something is actually kind of important, so you need to memorize it. And we'll apply it in this case of thin film interference, where we want to determine the conditions where destructive interference occurs. So what we're having is that we have coherent light that shines through here on top of the film, contacts this mirror, reflects out. And you want to see when these two destructively interfere. So if you want to do that, right, we want to basically equate your OPL to be your sum m lambda or m minus half lambda because this is what causes the phase difference between the light rays So the difference in OPL, right, because we're assuming this angle is super small, your difference is NT Yeah. Oh wait, actually it's twice NT. Sorry, this is a mistake. I might need to change this. Yeah. So the difference in optical path length between the two rays is twice of NT. So because of that, right, so your difference in optical path lengths between the two rays that are emitted is 2 times NT, right? So this causes a phase shift. And usually for disruptive interference, you would have equated it to this. But actually it's not the case because you gotta remember that what we're considering is that here, right, this is the most optically dense medium here. So when this light ray comes in here and reflects here, right, there is a phase shift of pi radians that happens for this light ray. But for this light ray, right, it comes in here, it refracts through, there's no phase shift. It reflects off this, but this is a less optically dense medium, so there's no phase shift here. And then it refracts out, so there's no phase shift. So overall, right, there ends up being a pi radian phase shift due to this. So when you account for destructive interference, right, you need to add this extra phase shift to account, which comes from the reflection here. So you get that your destructive interference condition is actually 2nt is m lambda. Yeah. So this is something you need to take note of. Yeah. And note that this actually implies that if your thin film is sufficiently small, your film is actually completely dark, because these two will destructively interfere because these two will destructively interfere because your OPL through here is insignificant, but there's a there's a pi radian phase shift because of this so then they will destructively interfere in a dark. Yeah. Okay, that should be it for geometrical optics. Are there any questions about this? Okay, if not, I'll go on to the last part of this notes. It's so long, which is geometrical optics. So geometrical optics, right? Just now we have previously dealt with stuff like interference and superposition. But when we go to geometrical optics, right, we're now going to discuss light propagation by rays. So when the scale of this is when the scale of consideration is much larger than the wavelength of light. So as you described just now, we have reflection and refraction. And it comes from this thing called Fermat's principle, which basically states that the path taken by light between 2 points is the one that takes the least time. And it can also be rephrased in terms of optical path length if you realize that this a bunch of math, but basically it just says that your Fermat principle can also be rephrased as your light ray wants to minimize the optical path length that it takes. Yeah. So because of this, we end up with three things that we can conclude. The first thing is that between 2 points A and B, they are unobstructed, right? Light will take the direct path to it, so it's a straight line. And this is obviously because the shortest distance between 2 points is a straight line. The second is the law of reflection. If you want to have a light ray going from A to B that is not direct, it has to hit this mirror somewhere, right? It will want to take the shortest path, right? And the shortest path comes from when you take this endpoint, you reflect it across the mirror, and you draw a straight line through it. This is going to be the shortest distance, right? Because this distance and this distance are the same. So any other path that you take, like for example, like this, right? It's going to take a longer distance because this distance from A to B prime is not shortest. So the shortest must come from when it's directly from A to the image of B, like this. So if you do some geometry, you get that these two angles are equal. Yeah, and that's basically just the law of reflection. The angle of incidence is equal to the angle of reflection. And one more thing that you get is the law of refraction, which basically the math is omitted here. But if you do the math, right, and you consider the minimum optical path length that a light will take from A to B in two different refractive indices, right, you get this law, which is that your refractive index multiplied by the angle of incidence is the refractive index to the next one, multiplied by the sine of the angle of refractance, the angle of refraction. Yeah. This is called Snell's law. I think you should know Snell's law, basically. Yeah. So these are the laws of reflective refraction as well as Fermat's principle. Fermat's principle is actually pretty useful in certain situations, which I might illustrate later. And of course, light doesn't generally just purely reflect or refract, because usually it will split into two beams of different intensities, when one is a reflected and one's a refracted. So here's one example. And this is illustrating a concept called apparent depth. So we suppose an object is suspended underwater in neutral equilibrium, right? And you're reviewing it from the top. Basically, what you're trying to find is this thing called an apparent depth, which is basically how deep it appears to be. And the reason it doesn't appear to actually be at height h below the water, right? It's because of refraction. Because if you look at your eye here, right, your humans only really sort of they only perceive light to travel in a straight line. So your object will actually appear here instead of where it actually is. So in order to calculate the apparent height, right, you can sort of do a lot of math, right? And then you do a small angle approximation. This should not be here. This should be further up. But you can get your apparent height is this. Yeah, you can read through the example yourself. It's just some math and some basic consideration of the angle of incidence and refraction. And we have total internal reflection, which is that basically, right, if you notice from Snell's law, right, if you're traveling from an optically denser medium to optically less dense medium, right, at some angles, right, this thing can no longer be satisfied. So that means there will be no refraction that occurs. And what happens instead is that the light beam, right, is completely reflected off the surface, where this is the less optically dense medium. And this is called total internal reflection. So what you can do, right, is you just solve for the fact that at the boundary, right, this thing must be one, because it cannot be more than one. So then when you solve, you get this thing. And this thing is called the critical angle. So at the critical angle, right, once this angle is more than a critical angle, it only totally internally reflects. Yeah. This is called total internal reflection. Yeah. Okay. Now we get to spherical surfaces. Because spherical surfaces turns out to be pretty important. I'm not too sure how important in SPhO. So I would suggest that the reflection and refraction of spherical surfaces are not actually too important. But lenses are important. You need to know lenses. You need to know lenses. Definitely need to know lenses. So I'll just touch on these. So basically, basically, what we do is that we sort of derive the properties of the reflection of a spherical surface. So if we have an object over here, right, we actually have an image that's formed because of the reflective surface. And that's the same as a mirror. If you have an object here, right, you have an image here. So this is actually the image that's formed by the mirror. So how exactly you determine the image is by using ray diagrams. If you have a spherical mirror, right, and we have a spherical mirror with a center, right, you can consider three rays that emanate from the object. One is this ray here, which is parallel to the principal axis. And it reflects through the focus. And this is sort of the definition of the focus. Because the definition of the focus is that parallel light rays will reflect onto the focus. The second thing is one that passes through the focus. A light ray that passes through the focus will reflect parallel to the principal axis. And again, it's by the same logic, because if you had a light ray that came here, it will reflect through the focus. Yeah. And the last thing is that if a light ray passes through the center of the mirror, if it passes through the center of the mirror, this angle is parallel. Sorry, this angle is perpendicular. So then it will just reflect directly back. So it turns out, right, that all these three rays will intersect at one point, and this one point forms the top of the image. And it turns out that any other ray that reflects off this mirror will point through this image. Assuming that they are parallel axial, meaning like these are super close to the principal axis. So that's sort of how an image is formed by spherical surfaces. And you can go through all this reading yourself. I'll let you do it by yourself. But you end up getting these equations, which are called the mirror equations, and they sort of describe your position of the image and your position of the image and the object, as well as the height of the image and the object. So if you're given, for example, this S, right, and you're given the focal length which can be determined from the radius, right, then you can eventually determine the position of the image as well as its magnification, something like this, yeah. But I will just touch on this because it's not really too important, yeah. And these equations hold for both concave and convex, and in that case, right, your radius will have different signs, which I'll let you read through this whole chunk of stuff talking about the sign conventions for quantities, yeah. It's not too important, so I'm not focusing too much on it. Second thing is refraction, which I think is even less important on its own, if I'm gonna be honest. But I'll also just go through. What happens is that you have a similar situation here, right? Where your light, you have three principal rays. One where it's parallel to the principal axis and passes through the focus. One passes through the focus and ends up parallel to the axis. And one passes through the center, in which case there is no refraction now. And again, it will form an image because they're all concurrent. And one thing to note about refraction, right, at the spherical surface is that there are actually two different focuses. I mean, there's always two focuses, but here, right, your two focuses, right, are actually at different distances from the vertex, actually. So yeah, that's for refraction. And again, different sign conventions, actually, blah, blah, blah. You eventually can get these equations for refraction at a spherical surface. Yeah. Again, not too important. But what is important if you're going to get through lenses, because lenses are quite common. So lenses are typically a focusing device. So how it works is that where's my mouse? If you have a lens like this, right, and you have an image like this, right, when it comes out of the lens, right, you have an image, something like this. And it turns out that the properties of the image can be determined by these equations here. These are actually the same equations as the mirror that we saw just now. But here, basically, it gives you the relationship between the distance of the object, distance of the image, height of the object, height of the image, as well as the focal length of the lenses. And if you have the radii of the lens, right, you can actually determine its focus, as well as if you know its refractive index. And this is called the lens maker's equation. Yeah. So yeah, from the lens maker equation, you can get the focal length. And from the focal length, right, you can determine the position of the image if you're given. And these lenses can be categorized into two main categories, which are converging and diverging. Yeah, and they have the converging one has a positive focal length, and the diverging one has a negative focal length. So a converging one will look something like, a converging lens would look something like this, right? In which parallel light rays are focused onto some focal point. Or a diverging lens would look something like this, in which case they're not actually focused, they're actually diverging, but they will meet at a focal point in front. Something sort of like this when extended, but they don't actually meet, they'll all diverge. Yeah. And when you consider ray diagrams, right, these same principal rays are also important. One is this parallel to the principal axis, passes through the focal point on the other side. One is passes through the first focal point and then comes out parallel. And then one is through the center, in which case it doesn't refract. So they will all intersect at one point, and this point forms an image. Yeah. There's really too much to cover. So I really suggest you reading through this section yourself, because these lenses are kind of important, but it's quite difficult to cover in such a short amount of time. But the ray diagram is definitely important, and these equations are definitely important, and the lens maker equations. You need to remember all these. Yeah. And one more thing to touch on for this is variable refractive index, because what we have from Snell's law is this is true, right? So if we consider something like this, right? Let me see how much I can zoom. If you consider something like this, right? Your this n sine theta 1 here, right? This n1, n2, n3. And this refracts through here, right? This is your theta 2, right? Your n1 sine 1, these two are equal by Snell's law. But this angle here is also theta 2, right? So then when it goes through, right, something like this theta 3, this is also equal to n3 sine theta 3. So what you can conclude, right, is that another way to rephrase Snell's law is actually that the refractive index multiplied by the angle to the normal is constant. And this is very useful when you have cases of variable refractive index. So one example I can give is that they ask you to show that light travels in circular arcs in a slab where the speed of light varies linearly with height, which seems quite difficult to prove, but you can prove it using this formula here. So what we have is that in this slab region, you can think of this as having varying refractive indices. So the higher you go, the higher you go, the less refractive it gets. That's right, the less optically dense it gets. So what we do in this case, right, is that we let the speed of, since the speed of light varies linearly with height, right, we will let the velocity of light be this. So then your refractive index actually turns out to be this. So when you have that, right, you can use this fact that n sine theta is constant to sort of substitute in here, and you get this equation, right, which turns out to be solved to be this equation. So how exactly you get the fact that it's a circular arc? It's because this implies a circle. Why? You think about this, right? You look at this diagram here, right? This gives your basically opposite over hypotenuse lah. Your hypotenuse is this lah, which sort of gives that this is the radius of your circle lah. And this is your opposite, which is basically this height lah. So basically at all times, since this is satisfied, right, your this light will follow this circular trajectory lah in a radius of radius y naught times cosecant theta naught lah. So that sort of gives your conclusion that light travels in circular arcs. It's not a very rigorous proof. So you could obviously prove it rigorously, right? By doing something like c over alpha y sine theta relating to this, right? Because your dy d theta is tangent theta, right? So then you could relate it to like, I don't know lah. This would be sine of tangent inverse dy dx lah. You can simplify this to something lah, and that equals to a constant lah. Then from there, right, you'd have a differential equation which you then solve lah. Then once you solve the differential equation, you can eventually equate it to be a circular arc lah. Yeah, but I will not do it lah. And you can already see intuitively from this equation, right, that this basically just says sine theta is y over r lah, which is exactly what is the case in circle lah. Yeah, that should be the whole notes. Are there any questions? I'm sure there are some questions. Okay, if there are no questions, right, I'm gonna start going through the problems slowly. Why is it equal to r? I can't see that. Let me go back. So you look at this, right? Let's say you have a circle like this, right? You have that this angle here, we let this be theta lah, right? This is y, this is r. You have that by trigonometry, right? The sine theta is y over r. Now we look at this situation for this, right? Here we define the angle of incidence to be this. And you notice that, right? Here we define the angle of incidence to be this. But it turns out, right, that we can also equate this to this angle of incidence here because these two are perpendicular. So if you take this thing and you rotate it 90 degrees, right, your this rotates to become here, your this rotates to become here lah. So these two angles are equal lah. So you can see this is y and this is your r. And your this r, right, comes from this lah. So this will be your r lah. So you have that the radius of your circle is this lah. Yeah. It's not really a very concrete explanation lah, but it's more of an intuitive explanation to sort of show you why the light will travel in a circular arc. I don't really want to dwell too much on the rigorous proof lah, but I think you should be able to kind of see why it's equal to r, right? Yeah. Okay, now I'll go through I'll go through some of the problems. Are there any problem requests other than the ones I've already received? I'll go through some of the problems here. Seems like this one also wants to be going through. I've already highlighted some of the more enlightening ones that I think you should go through. But if there are any other problems, please raise up now. If not, in like a minute or two, I'll start going through the problems that I've chosen. The SPhO problems I won't really go through because most of this is mostly math bashly lah. So you should be able to apply the stuff lah. Now apply the formulas that are in the form that are in the notes at least. but the more enlightening ones I'll go through. Okay, if there's nothing else, okay, if there's nothing else, right, I'll just start going through the problems. Okay, so the first problem I'll go through, right, is this. So basically, the question states, right, from above, right, coherent monochromatic light of wavelength this illuminates a convex curved glass of radius of curvature r. So this is some radius r, and it lies on another flat piece of glass. So it turns out, right, that because of this, right, it forms a diffraction pattern on this glass, and this is called Newton's rings actually. So what we want to do is we want to find the radius of the nth bright ring of the diffraction pattern. So how exactly do we go about it? Let's zoom in into the diagram lah. So this is going to be one segment of this curved glass of radius r. Let me see if I can draw it better. Yeah, so this is a super zoomed in version now, and this is r. So what happens, right, is that what we're going to do is, actually, you know what, I'll draw it even flatter because the flat bar is actually important. Something like this. So overall, this is some radius r, whatever. But yeah, so how it works is that the reason there's diffraction patterns is because there is actually a phase difference between the ray that comes in like this and the ray that comes out like that. So these two rays will actually interfere with each other. So it's very similar to thin film interference lah. Yeah. And the sort of phase difference comes from this extra air gap in here. And what we're doing is that we're assuming that this R is super big lah. So because of that, like we're not really considering the angle of refraction or whatever lah. We're basically considering everything to be almost completely vertical. So how exactly do we calculate the radius of the nth bright ring? What we do is we obviously we use the same thing lah. So because okay, yeah, because here, right, it turns out that there's actually no phase shift. I think. Oh no, there is a phase shift because here's the air, right? Here's the glass. So here, when this light ray reflects off this glass, right, there is a pi radian phase shift, right? However, here, right, when this reflects off here, right, this is from glass to air. Air is less dense, right? So when it reflects, there's no phase shift. So what we're gonna do is that we need to equate the the difference in optical path lengths between the rays to be your constructive interference condition lah, which is m lambda, but we subtract half lambda because of this pi radian phase shift. So we want to find the difference in OPL now. So to find the difference in OPL, right, all we need to do is consider the geometry of the system. So if you look at this, right, this is a radius r, right? So you can essentially consider it as a circle, which is described by this, right? So if you want a height here, right, given this x, right, and your x is actually the radius lah. So we actually can solve for y lah, and we get y is r minus square root r squared minus r squared, like this. So this is your height of this thing lah, right? And because we're considering in the limit of being very, very close, right, we can sort of first order approximate this lah. So we can do this by factoring out this big R, right? So we get 1 minus 1 minus R over R squared, right? So if we take the first order approximation, we get R half R over R squared, which is small r squared over 2 big R. So we actually get that you can sort of approximate this height as this. So now, right, when we consider this equation, right, your OPL should be m minus half lambda. Remember, the half comes from the fact that there's a pi radian shift, and we want constructive, right? Your OPL is this, because it has to go down and up, so it's times 2, and it's an air, so refractive index is 1. So OPL is this, equals to m minus half lambda. Actually, this should be n, because we want the nth ring, right? So we get r is square root of lambda r n minus half. That's your answer, lah. So that's your radius of the nth right ring, lah, of the diffraction pattern. And that's called Newton's rings, lah. Yeah, if you Google it, you should be if you Google it, you should be able to see the same derivation, lah. Yeah. So that's Newton's ring. The guy who clarified this question, do you understand? Do you understand the solution I've given? Didn't get the approx. Yeah. The approximation is a bit funny, lah, for Newton's rings, lah. But basically the assumption we're making is that we're not really considering the angle of incidence of refraction, lah. So it's basically vertical. And the approximation comes from the first order approximation, lah, because we're already considering it flat. We're almost flat, lah. So you can take this approximation to be quadratic, lah, like this. The first order yields a quadratic function, lah. And then from there you can determine the OPL. Yeah. Okay, next question I'll go through this one.
So this one, I think it's an enlightening question that you guys should know how to do. So you have a coherent light source and you have two mirrors, right? And what you actually realize is that there is diffraction at the right line.
There's diffraction somewhere here. So why is there diffraction? There is no double slit or single slit here, right? You might think. But actually, right, the important thing to do is that you need to consider the mirror images. Because of the source here, right, there is actually a mirror source here and here, right? And these mirror sources, right, emit their own light. Something like this. So even though there's no double slit here, right, there is actually a double slit formed by the mirror images. Because you can think about these as being slits, right? Light coming through, right? And then by Huygens principle, right, these will emit their own, these will be their own sources, right? So basically, these two mirror images of the source basically act as their own double slit, lah. So then this basically becomes a double slit problem. So how we do it is that now we consider the geometry, right? This angle here is also alpha. So this length here is a cos alpha. This length here is 2a cos alpha. So we have that the half distance between both of this is 2a cos alpha times sine alpha, which is a sine 2 alpha. So therefore, we have the distance between the two slits, right? D is 2a sine 2 alpha, right? That's one thing about a double slit down. The second thing is the distance L, right? And your L is going to be this whole distance here from the double slit. So your L, you can determine it to be, because this is 2a cos alpha, right? So this length here is 2a cos squared alpha. So your total length, right, is 2a cos squared alpha plus a, which you can use trigonometric identities. You can get a cos 2 alpha. Yeah. So now you have this, right? What does the question say? The distance between consecutive stripes is d. Oh, great. I shouldn't have used d. Let me use b. Fine. So your b is this and your l is this, right? And your distance between the stripes is d, right? So if you want if the distance between the stripes is d, right? Remember the formula we had, right? your delta y. Your delta y is basically your d, and that's lambda L over d. Okay, it's actually b, right? So now we have your lambda. Your lambda is b d over L lah, which is 2a sine 2 alpha times d over your L, which is a cos 2 alpha. So you get 2d tangent to alpha lah, and that's your wavelength. Yeah. So that's this question. Basically, what I want you to take away from the question is that even though there's no double slit, these two images basically give you a sort of double slit effect lah, because and you know they are in phase lah because it's symmetric lah. All this is a coherent source, right? So these two images are gonna have the same phase lah, basically. So you can treat it as normally and you can get that lah. Yeah. Next question I want to go through is this. This is actually from an SPhO problem, but
I think it's one of the easier problems if you know about waves.
so what you're doing is you're considering an elastic string that is stretched between two fixed ends, right? And you're given stuff like your linear mass density, and as well as the speed of transverse waves that are in the string is c lah. This length is L, and the string is plucked sideways like this. So the two questions, right, are firstly to find the period of vibration of the string and plot the shape of the string at this time. And the second question is you want to find the total mechanical energy of the vibrating string. So how do we do that? Sorry. First thing you want to do is you want to find the period of vibration. This is actually the easiest part. Because, right, recall what I talked about all the way at the beginning about two fixed ends. Because of two fixed ends, right, you basically sort of have this periodic function like this that you can consider to be released from rest, right? So go back to the problem. You can essentially consider your resulting wave to be a superposition of, this point is A and B, right? A superposition of this, right, moving to the left, and a superposition of this, the exact same shape lah, basically, moving to the right, not B, C, right? So basically, once you release this string from rest, it's going to be the superposition of both of these waves. And each of these heights, right, is h over 2 lah, because you got to remember this, it splits into 2, right? So how do we find a period? It should be pretty obvious, right? Because now you notice that this total length of this repeating segment is 2L, right? So one period will be defined by this whole wave moving essentially one wavelength, right? So after one wavelength, right, this point will reach back here, and you would essentially reach the same, you obtain your starting position lah, and the same thing for this right moving one lah, because it's symmetric. So because of that reasoning, right, you directly get your period of vibration of the string, right, is 2L over C directly. So that's one question solved. Okay, and they also ask you to plot the shape of the string lah at T over 8, which should not be too difficult, right? Because you know your T over 8 is L over 4C, right? So essentially, right, one of this would have moved over by L over 4. So if the original wave looks like this, right, one wave would have moved over by L over 4, and one wave would have moved over by L over 4. Something like this. And you got to remember that these also extend downwards, lah, essentially. Yeah. So when you add both of these waves up, right, you get that your shape of your string will look something like this. Because you can see, right, this flat part occurs in this region, where the sound of this will both end up like this. And the height of this flat part is, I think, half. Yes, h/2, right? And then the length of this part is L/4. The length of this part is L/2. And the length of this part is L/4. So yeah, just by that reasoning, right, and you consider the superposition of both, right, you already solve one part of this question. Yeah. Then the second part of the question, it says, find the mechanical energy of the vibrating string. Well, this should be even easier, actually. Why? Because you don't have to consider the motion of the string. The motion of the string conserves energy. So all you have to do is you need to consider the total mechanical energy to start, right? And what's the start? At start, right, your string is at rest. So if your string's at rest, right, the energy only comes from your potential energy. And your potential energy is, remember, right, it's half times the tension times dou y dou x squared dx. This is from the potential energy I talked about just now. It comes from your tension as well as your extension of the string. Yeah. So this is your potential energy, right? Which you can calculate to be your tension, right? Remember that this is a string wave. So your C is square root T over mu, right? So your T is mu C squared. So you get half mu C squared. What's your dou y dou x? That's basically the slope, right? And remember that this increases by height and it goes by a length of L/2. So this slope is 2h over L squared dx, right? So that gives, I don't know, but we integrate the energy over, right, from 0 to L, right? And on the first half, right, this is positive, this is negative, it's squared, so it doesn't matter, right? So you integrate this from 0 to L, right? And what you end up with is that the total energy is 2 mu c squared h squared over L. Yeah. So this is your whole total mechanical energy of the string. Yeah. So there you have solved this one part of the SPhO problem lah. Yeah. So this part is like, so this is just a really simple illustration of the solution to the wave equation as well as the mechanical energy lah. Yeah. Okay. Next, I'll go to this.
This one I don't actually have a solution, but this one illustrates an idea where we're talking about focusing.
So the whole time, right, when we're talking about lenses and reflection of the surface, right, we were using spherical surfaces. But the thing about spherical surfaces, right, is that they only actually properly focus, right, when they're paraaxial. So something like this. The thing about spherical surfaces, right, that the further you are from thing, right, the less focus it's going to be. And that's illustrated in this diagram here. This is what happens when you use a spherical surface. So they don't actually focus properly. So what this question asks, right, is they ask you to determine, right, what kind of curve does this at the end need to be? And honestly, it's kind of a bit of complicated math, so I don't really want to go through it. But if I'm not wrong, when you go through it properly, right, you should end up with a parabolic expression. Because parabolics are actually very special, basically. I think I can kind of roughly go through it. Basically, right, okay, I can give an intuitive explanation of it, but the actual math, right, I will let you do it yourself. But basically, right, the property of a parabola, right, this is solved by definition, right? A parabola has a focus and a directrix. This is a focus, and this is a directrix. So the special thing of a parabola is that these two lengths are the same at all times. So something like this, right? This length is also the same. This length is also the same, right? So because of this, right, turns out that this has the property that any line, right, that comes in from above vertically, right, when it reflects off the parabola, it is actually ends up at the focus. So something like this. And you can derive it yourself. This is actually a really special property of parabolas. So when we apply it here, right, a very similar thing occurs, I think. If I'm not wrong, that's how it works. Yeah. So if I'm not wrong, this should be parabolic for that same reason. Because if you consider the focus, this thing reflected backwards. Something like that. Yeah. I don't really want to go through the math because the math is kind of tedious. But if you want to go through the math yourself, what you can do is you can use Fermat's principle. Because Fermat's principle basically states that, if you recall, right, Fermat's principle states that a light will want to take the point, will want to take the path of minimum optical path length, right? So actually, I can just do the math right now. So by Fermat's principle, right, let's say we consider a source that's super, super far away from the lens, right? That means the light that eventually ends up reaching the lens, right, you can consider it to be basically almost parallel. Okay, so it's basically a source that's super, super far away. And it ends up getting focused at this point F, right? By Fermat's principle, right, light that comes here and ends up at this focus, right, if you consider this to be point A and B, right, it wants to take the path of minimum optical path length, right? However, right, since all light rays that come from here end up there, right, this must imply that the optical path lengths of all of these paths are the same. So that's actually a really really useful fact, because all we need to do is we need to equate the optical path lengths, right? So if you wanted to do the math, right, we can do this, right? Here, right, your x is a function of y, right? So we consider, let's say this is the x-axis, sorry, this is your y-axis, this is your x-axis, and your focus is at a point F from the start, right? So what we can do is then we can use this fact that the optical path lengths are equal. The optical path lengths for the light before it contacts here, they're all going to be the same, essentially, because we're considering it super, super, super far away. So we only need to consider the optical path length from here, for example, at some height y to here, something like this. So then what's the optical path length of this length? The optical path length, right, is the first thing we need to consider is refractive index n, right? So if n multiplied by this length here x, y. That's one equation you have, right? That's the optical path length through this part. Then your optical path length through the next part, right? Which, if I'm not wrong, we can make an assumption. Okay, I'm not too sure about the assumption, but I think we can assume that this distance is much, much less than this. In which case, right, this distance is square root of f squared minus y squared, I think. Yeah. So this is the optical path length that this line goes through, essentially. And what we have is that this should be a constant. And what's that constant? We can consider through like the very straight. So it'd be like nx0 plus f. So this is the equation that we get. And from there, I guess you can solve. I'm not too sure if you get a parabolic function. I might be wrong about that. But you can do the math yourself to get. Okay, not exactly a parabola, I guess. But from here, right, now that you have this equation, you can then solve for xy exactly lah, yeah. Or you can take away the assumption that this thing is super short. And then from there, you get nxy plus f. The thing is that it becomes more complicated to solve because now you get f minus x y squared minus y squared equals to this. And then you solve lah. It gets a little more complicated lah. It depends on what assumptions you want to take. But basically what you eventually get is that it's not a circle lah. Yeah. And most likely it's going to be approximately parabolic lah, because of these special properties about parabolas lah. Yeah. That's what I want you to take away. I know I explained it really weirdly. Is there anything you need to clarify for the person who's wait, but in the middle it looks like the path length is smaller than the one from the top. In the middle, it looks like the path length is smaller than the one from the top. It looks smaller? What do you mean it looks smaller? Okay, no, because you have to count for the refractive index, right? Because, where was I? Here, right? Here, this part is shorter than this, right? But it's accounted for the fact that over here, right, this travels more distance than here. So in the end, right, you should end up that the optical path lengths are the same. Yeah. And this is also multiplied by n some more. So overall, when you solve, right, it should be correct. You said the optical path length be equal for all points. Yeah. The time taken must be the same, and it's equivalent to the optical path length being the same. It's literally equivalent. Yeah, that makes sense, right? Yeah. So that's how you solve the question. Maybe I was wrong about a parabolic thing, but I think it should be approximately parabolic because parabolas are special. Yeah. Okay. I think the last question I want to go through is this. This is a really, really interesting question. Because what they do is they give you a linear source AB and then image through the thin lens A prime, B prime. And they want you to construct the lens and its focal points. So it might be quite intimidating. And to be fair, I was kind of stumped when I saw the problem the first time. But when you realize how to do it, right, you realize it's deceptively simple. And all you need to do is you need to know the properties of lenses. So let's first go back to a normal drawing of a lens. Something like this. Let's suppose we have an image like this, right? And we have focal point here and here, right? Three principal rays, right? One is like this, one is like this, one is like this. They all intersect at this point, which forms the image, right? First thing to note, this principal axis, this center, wait, this line through the center is completely unrefracted, right? So if you think about it, right, we have this line from A to A prime, right? Sorry. We have this line from A to A prime. This is going to be passing through the center of the lens because it's completely unrefracted, right? And we know that these 2 points eventually be connected. And the same thing happens for B, right? We know that the center of the lens lies somewhere on this line also, right? So what conclusion can you get from that? The conclusion is that your center of the lens must be here, right? So now we have one position, which is the center of the lens. The next thing we want to do is we want to construct the orientation of the lens, right? And this is a little more tricky, and I couldn't figure this out actually. But what you basically need to do to construct the orientation, right, is you now want to extend both of these lines. I mean, to be fair, you couldn't do much previously, but other than extend these lines. But let's say you extend these lines, okay? And they intersect at this point P. Okay. Special thing about this P is that the line joining P and C, right, is the plane, basically. It's the plane of the lens, essentially. Why is that? Because if you think about extending this point to B, right, you're going to extend this point B up until P, right? This is basically right in front of the lens, right? And you know that your image of B, right? If it's right up face right here, right? Your image of B is gonna be super, super close to it also lah, right? So this is your B, this is your E prime, something like that. So at this point, right, you gotta remember that it also passes the focal point lah. So when you go from A to B to P, right, your A prime goes to B prime. It goes infinitely far and it loops back around on this line because the image can't really escape this line. So then at some point, right, it will come back on this line and intersect here. So basically, what I mean to say is that these two lines must intersect at a point on the lens. So this P is a point on the lens. Oh, sorry. So this point P is on the lens, right? That means you now have the orientation of the lens. You can draw a line from P to C and pass, right? And you now have, this is the plane of the lens, right? And now you can construct the principal axis. The principal axis is just perpendicular to it. So like, let me use a different color. So now you have the center. You have the plane of the lens, and you have the principal axis. So now you have this, right? The final thing to do is to construct the focal points. How do you construct the focal point to the lens? This is even simpler, right? Because all you need to do, right, is remember that a line that passes parallel to the principal axis must pass through the focal point and intersect the principal axis, right? So all you need to do is do that, right? Let's consider point A since it's further up, right? We construct a line that is parallel to the principal axis, right? Can I use green again? Yeah, we construct a line that is parallel to the principal axis, right? And then it must reach A and intersect the principal axis, right? Yes. Intersects here, right? You can then deduce this is your focal point. Yeah, so this is your focal point of the lens. And you can construct the other one similarly, lah, right? Because similarly, a line that passes through the focal point here must come out parallel to the principal axis, right? So we can sort of backtrace it lah. Here, this line is, my God, this line is parallel to the principal axis, right? So this parallel. Then it will, we can retrace it to here, right? Then this is our focal point. So now we have both our focal point positions. And then we have constructed the lens as well as its focal points. So this is a pretty neat geometrical problem, I must say, because it really tests how to use these sort of properties of the lenses to sort of deduce its position, orientation, and its focal points. Yeah. Are there any questions about this particular problem? Okay, if not, right? If not, I've gone through all the problems I want to go through. Are there any other problems that you guys want me to go through? If you should, if you have any, you should raise them up now. Okay, it seems like nobody has any questions. If nobody has any other questions, right? I think I'll call it off here then. I'll let you off a little bit earlier. I think I'll just call the lesson off here lah. Yeah. If there's nothing else from y'all, if you want to stay back and ask questions, it's okay. If not, then I think I'll end the lesson here and you're free to go. Yeah, thank you for coming.
Thank you.
Thank you.